So the small signal model of the MOS transistor would look somewhat similar to the NPN transistor, but this time we don't have that R pi because there's no current going through here, so there's no the input resistance would be infinite, but we still have that GM and RO. So our RO here is 1 over lambda times ID, and the GM is the current capability with respect to the gate source voltage. So if you take that derivative, it would be nu n C aux W over L VGS minus VTH. This would be in square root nu 2 nu n COX W over L times ID. You can either use this one or that one. So coming back to the common source stages, so there are basically 3 common source stages we can use. Okay, this is V in, V out, RD. One with just the resistor, one with a PMOS transistor with a bias voltage. So instead of using a resistor, this time we would use a transistor. The other one would be again a transistor, but this time a diode connected transistor. So I'll label them. This is 1 and 2, and 1 and 2. So we'll talk about the gain, input and output resistances. So input resistance are all the same, and it's infinite. When it comes to the output resistance for R out, here we have the RD in parallel with RO. Here we have again the RO of the first transistor M1, but this time it will come parallel with RO2. And here is RO1 parallel with RO2 in parallel with, because we're looking at from the source, it's going to be the GM of the second transistor. And usually 1 over GM is the smallest one, so this would be more like 1 over GM2. And your gain would be given as negative GM1 R out for all of them. The only difference, if we use the source degeneration, in this case, our R out, similar to, let me write it down here, our R out would be again the RO in parallel with RD, the output resistance as if there was no source resistance, but it will be multiplied by 1 plus GMRS. So this is your output resistance would increase. And your gain is given by the RD in parallel with RO divided by 1 over GM plus RS.